Hello. So we are talking about the properties of dosimeters. Another property is the linearity. What does it mean, linearity? Here, the dosimeter reading should be linearly proportional to the dosimetric quantity. So, of course, the reading of the dosimeters should be linearly proportional to the dosimetric quantity. Beyond this certain range, usually a nonlinearity sets in. This effect depends on the type of dosimeter. So the dosimeters differ in linearity property. Each dosimeter has its own specific characteristics and properties, and the linearity range. We have two possible cases here. We can talk about a linear dosimeter or supralinear, or we can talk about a saturation. This is case A. So in case A, we have linearity, then we have supralinearity, then we have saturation. Saturation means that the dosimeter reading becomes constant. It doesn't vary after a specific amount or after a specific amount of dose. So if the dose increases further, the dosimeter reading stays stable, constant. This is saturation. بيوصل لمرحلة ما بيعود الدوزيمتر يقرا أكثر من هيدي الليفل، أكثر من هيدا الدوز ليفل. سو بعض انواع الدوزيمتر بيكون عندهم linearity بالبدايه، بعدين supra linearity، بعدين saturation. هلا عندنا another case linearity and saturation directly. So some dosimeters have linear property لحديت ما يوصل لليميت معين او دوز معين، بعدين it becomes saturated. So we have two types of linearity or two possible cases of in dosimeters. A third property of dosimeters is the dose rate dependence أو بنسميها MD. MD parameter أو MD property. So the response of a dosimeter, a response denoted MD, refers to the measured observed value. So measured or observed value divided by the actual dose. So M is the measured value or observed value, D is the actual dose. So M over D. فإذا M over D بتعبر عن الريسبونس of a dosimeter system. Measured or observed value divided by the actual dose of radiation that the dosimeter is exposed to. So this ratio represents the sensitivity of the dosimeter to the radiation dose. عادة بيعبر عن sensitivity of this dosimeter. When you are measuring an integrated response, if you are measuring an integrated response, you are essentially measuring the cumulative effect of radiation over a period of time. So we have here the integral over time, integral M over D, dd over dt, dt. So we are measuring the cumulative effect of radiation over a period of time. This principle stated that the dosimetric quantity being measured, which is M over D, should be independent of the rate of change of dose over time, which is expressed as dd over dt. So in simpler terms, the dosimeter's response should not be affected by how quickly the radiation dose is delivered. So dosimetric quantity should be independent of the dose rate. فإذا dd over dt بيمثل أو بيعبر عن الدوز rate. Other formulation, here we can see another formulation. So the response M over D should be constant for different dose rates, dd over dt1 and dd over dt2. The response M over D should be constant. So we can move M over D to the outside the integral. فإذا this principle can also be expressed as the requirement for the response M over D to remain constant regardless of the specific dose rate. بغض النظر عن الدوز rate, this amount M over D remains constant. So if you have two different dose rates يلي سميناهن هون dd over dt1 and dd over dt2, dosimeter response should be the same for both dose rates. The energy dependence is an additional property of dosimeters, so it represents the response of a dosimetric system as function of the radiation energy. So the response of a dosimetric system is a function of the radiation energy. Here we have an example about the energy dependence of radiographic film, of a full film dosimetry. هلا فينا نشوف هون ال density versus dose. كيف هيتغير for different energies. فإذا غيرت الانرجي مثلا من 1.71 ميجا الكترون فولت ل 79 كيلو الكترون فولت or 44 كيلو الكترون فولت or 28 كيلو الكترون فولت فينا نشوف انه the energy affects the result, affects the response of the dosimeter. فإذا term radiation quality is frequently used to express a specific distribution of the energy of radiation. Therefore, dependence on energy can also be called dependence on radiation quality. Dependence on radiation quality. We can use both terms. Since calibration is done at a specific beam quality, a reading should generally be corrected if the user's beam quality is not identical to the calibration beam quality. Here we have an example. So an example concerning the energy dependence property. As in here the concept of energy dependence is illustrated through the determination of absorbed dose using an ionization chamber. هلا طبعا ionization chamber is initially calibrated in terms of absorbed dose to water, typically using a calibration radiation quality such as the CO beam. So a well-known example of energy dependence is the determination of absorbed dose by this ionization chamber, calibrated in terms of absorbed dose to water. So we calibrate the ionization chamber or in terms of absorbed dose to water in a calibration radiation quality. So note that if the absorbed dose needs to be determined in a user beam that is different from the CO beam, an energy-dependent correction is necessary. This correction factor is referred to as the quality correction factor. So it accounts for the variations in the response of the ionization chamber to different radiation qualities or different radiation energies. فإذا in simpler terms, the ionization chamber's response to radiation can vary depending on the energy of the radiation. The initial calibration is specific to a certain radiation quality. And when dealing with a different quality of radiation, the correction factor is applied to ensure accurate measurements. إذن هذا correction factor addresses the energy dependence of the ionization chamber, allowing for more precise and reliable determinations of absorbed dose in various radiation qualities. We have another property of dosimeters يلي هي directional dependence property. كمان الدوزيميتر may exhibit variations in sensitivity depending on the direction from which the radiation is incoming. فإذا variation in response, the variation in response as a function of the angle of the incidence of the radiation is called the directional dependence of a dosimeter. فإذا هون فينا نحكي عن ال internal design and construction of the dosimeter. The internal design can influence its directional response. مثلا certain dosimeters may have components that interact differently with radiation depending on the angle of incidence. كمان the physical size of the dosimeter plays a role. Larger dosimeters أكيد larger dosimeters or those who with specific shapes may have varying responses to radiation. So they may have varying responses to radiation from different directions. فإذا orientation of the dosimeter radiation detector can affect its response, can impact its response. Some dosimeters may have a preferred orientation for optimal performance. فاذا الايونايزيشن تشامبر فاذا هي one type of dosimeters. في بعض الدوزيميترز بيكون بقلبهم ايونايزيشن تشامبر. هذه الايونايزيشن تشامبر بيكون بقلبها غاز، ممكن تكون filled of gas. فاذا الايونايزيشن of the gas due to incident radiation will generate a measurable electric current which is then related to the absorbed dose. هلا بهذه الصورة هنشوف كمان تأثير الانجل على الريدنج. The spatial resolution and physical size. So the quantity absorbed dose is a point quantity. We have what's called the quantity absorbed dose. This is a point quantity. We have ideal measurement. The ideal measurement requires a point-like detector. So in this case, the ideal measurement requires a point-like detector, as you see here in the figure. We have here in this figure a point-like detector. أو فينا نحكي عن systems مثلا مثل TLD that approximate a point measurement. في عنا TLD، في عنا الفيلم والجل system، pinpoint micro chamber system. TLD اللي هو thermoluminescent dosimeter. TLD هن عبارة عن small crystalline detectors that can approximate point measurements. They record ionizing radiation exposure. أكيد في process هنحكي عنها بعدين. هلا الفيلم and gel dosimeters كمان they offer spatial resolution and the point is defined by the resolution of the readout system. So these detectors capture the distribution of radiation exposure across their surface, allowing for detailed information about those distribution. Pinpoint microchamber. These are specialized ionization chambers designed with a very small sensitive volume. While not achieving a true point-like measurement, their small size allows for more localized dose measurement compared to larger ionization chambers. فإذا the term point here refers to a small and well-defined region. يعني هنحكي ب finite and small point. فإذا the spatial resolution is limited by the physical property of the detector. Achieving a true point measurement is often impractical due to the physical size and limitations of detectors. So the goal is to use detectors with small and well-defined sensitive volumes to approximate the point measurements as closely as possible. The choice of detector depends on the specific application and the level of spatial resolution required. يعني نحن بنختار حسب الابلكيشن وحسب السبيشال ريزولوشن يلي نحن بحاجه لها. So ionization chamber type dosimeters normally have a larger finite size. Measurement result corresponds to the integral over the sensitive volume. Measurement result can be attributed to a point within the volume referred to as effective point of measurement. So measurement at a specific point requires positioning of the effective point of measurement at this point. هلا في عنا الايونايزيشن تشامبر. فاذا اذا بدي احكي عن الدوزيميترز، هلا طبعا في انواع، في منهم ريوزبل في منهم not reusable. هلا الايونايزيشن تشامبرز are reusable with no or little change in sensitivity. حتى اذا استعملناهم كذا مره ما بيصير في تغيير كتير كبير بالsensitivity of these ionization chambers. في عنا انواع تانية مثلا semi conductor dosimeters كمان هن reusable and but with a gradual loss of sensitivity. وعندنا some dosimeters which are not reusable at all مثل الفيلم dosimeter مثل الجل and alanine dosimeters. And some dosimeters measure the dose distribution in a single exposure مثل الفيلمز والكيوت جلز أو الجلز. فإذا الفيلم dosimeter عادة عم نحكي عن photographic film that change in opacity or color in response to the radiation لما يتعرض للراديشن. Once the film is exposed, the changes are typically permanent and the dosimeter cannot be reused for another measurement. لهيك قلت هون الفيلم dosimeter is not reusable. فإذا خلص بس يتعرض لراديشن البروبرتيز تاعونه حتتغير ولونه حيتغير، فمنا قادرين نستعمله مرة تانية. حتى الجل دوزيميتر بيكون بقلبه عادة radiation sensitive جل. كمان بيصير في تغييرات بالفيزيكال بروبرتي اوف ذيس جل بس يتعرض لراديشن. يعني بيصير في تغيير بالاوبتيكال دنسيتي مثلا لما يتعرض لراديشن. So once the gel is irradiated, the dosimeter cannot be reset for reuse. ما بنقدر نستعمله مرة تانية. الاناين دوزيميتر هنحكي هون. الاناين هو امينو اسيد. كمان فيني اعتبر الامينو اسيد الاناين فيني اعتبره radiation sensitive material مثل الجل والفيلم. بس يتعرض للراديشن بيصير في تغيير بالبروبرتيز اوف ذيس الاناين دوزيميتر، وهدول التغييرات are permanent after exposure. يعني ما عاد قادرين نحن نستعمل الدوزيميتر مرة ثانية. So reusable dosimeters that are rugged and handling doesn't influence their sensitivity are الايونايزيشن تشامبر. الايونايزيشن تشامبر هي reusable dosimeter. وهلا ما عدا الايونايزيشن تشامبرز with graphite wall. فينا نحكي كمان عن reusable dosimeters that are sensitive to handling اللي هن thermoluminescent dosimeters TLDs.